Well, hello everyone, and welcome back to Prep 10. So now we're going to explore the relationship between days missed and sales calls. So it's still inferential correlation. We're looking to see if there's a relationship in the population. Actually, it'd be interesting to see if there's a relationship in the sample because it's a near horizontal line. So an analyst wants to determine if there's a relationship in the population between days missed and number of sales calls, which kind of seems reasonable, right? If you miss a bunch of days, maybe your calls would go down. But let's see if that turns out to be true. They take a sample of 10 employees and collect their data. So the case is going to be two-tailed, because it always is. We have correlation. The distribution is T. Null hypothesis is that it's going to be a zero correlation, and the alternative would be not zero. So let's go ahead and calculate the correlation. Which is 0.004, so not much there. And then count. And degrees of freedom is going to be the count minus 2. All right, the sampling distribution of R, the mu, would be that it's 0. And then the standard error is going to be equal to the square root of 1 minus R, get it right this time, squared, divided by n minus 2, which, as I mentioned before, is really just the degrees of freedom, 0.35. And so the observed difference is going to be equal to the correlation, which isn't much. I'll put that out one more decimal point just so you can see that it really is the same 0.004 here. And then the t-score is always the observed divided by the standard error. And that's a pretty small t-score, and the probability of t, it is positive, so the probability is t.dis.2t. So 99%. All right, so this is not going to be a reject because we are effectively almost dead center. But let's go ahead and continue the whole thing. So alpha is 5%. And then this is going to be t dot inverse probability and degrees of freedom. Remember, we lock the degrees of freedom to make it easy to copy across. And then over here, we do 1 minus for the right tail. And the correlation here is this guy there. And then we take, again, I'm going to add a decimal point so you can see that it really is the 0.004. And then we take that number and subtract from it the standard error times two-tailed right. So no need parentheses. All right, and then for the upper bound, take that number and add to it the standard error times the two-tailed right. And since both of those are within the -1 to 1 range, we can just reference them. Here we don't have to redo any of them and actually make it 1 or -1. All right, so huge confidence interval, which includes mu 0, mu null, or the null hypothesis. So no way this is a reject. And so our conclusion is fail to reject. It's a lot greater than alpha. It's the same population and less extreme than the critical value. And the interpretation is that the correlation is still zero in the population. We can't say that it's not. And it's possible there's a type 2 error, but really, really, really highly doubtful in this case. So what do you learn from this? You learn, well, in this case, if there's almost no correlation in the sample, it's very doubtful there'll be a correlation in the population. In fact, you expect just the opposite. You would expect that you'd have to have a fairly good correlation in the sample before you can make the jump to say that there's a correlation in the population. And that's it for this one. Now we move on to regression. And so in regression, we use the sample to make a predictive claim about the population. So this is new. We're actually trying to predict things, because now we're trying to establish the regression line. We're no longer just interested in how close the dots are to the line, but we actually want to know about the line itself. And this assumes that the independent variable predicts the dependent variable. The independent variable is here on the x-axis, and the dependent variables on the y-axis. And looks to provide some evidence that this could be true. However, it does not prove causation, right? We are going to be able to establish that there's prediction, but we can't prove causation. Why not? Because there could be other variables that might be affecting everybody. Nonetheless, test to see if the independent variable can be used to predict the dependent variable. That's what we'll be doing. So an analyst wants to determine if the number of sales calls can be used to predict the number of copiers sold. They take a sample of 10 employees and collect their data. Alpha is 5%. So notice, same data set, right? But this time we're doing something different with it. So select the test is going to be SLR, simple linear regression, the individual test. There's also a global test, which you would use in multiple regression, but since we're not doing that, we're jumping right to the individual test. Identify the case, and the case is going to be two-tailed. H0 is that the slope is not significantly different from 0, and H1 is that it is significantly different from 0, and that's why it's two-tailed, because we don't know, right? I mean, here we have the picture, but but we really don't know for sure if that line's going up or going down in the population. All right, at least at this point. Alpha is 5%. All right, the t-stat. Now this says reference, because now instead of doing calculations in this one, we're actually going to use the data analysis toolpack to do the calculations for us, because the calculations in regression get a little bit hairy. So we go ahead and go back to data analysis. This time it's not correlation, it's regression. Then we pick the y range. Remember, y is the dependent variable. What's on the y-axis? In this case, it's copiers sold. It's also what's being predicted. If you didn't have this little picture, you'd get it from whatever's after the word predict, right? So sales calls can be used to predict copiers sold. That's why it's the dependent variable. It's what's predicted. And then the x variable is what is used to predict it, which is sales calls. And there are labels, and the output range is right there. Click OK, click OK. Then we get some pretty big output. Now, again, hard to read the numbers, so what we're going to do is, starting with the first number, highlight everything, and then let's just bring in the decimal places just so it's kind of easier to read and work with. We'll go to 2 decimal places. So there's our correlation coefficient again, right? Here it's called multiple R. but since there's only one predictor, it turns out to be the same as the correlation coefficient. And there's that 0.52 that we've seen on all the graphs, which is also called the variance. So 2 numbers right away that are very familiar, and then a lot of numbers that are not familiar. Well, I'll stay here for a second. So this part in the middle, the ANOVA, this is what we would be very interested in if this was multiple regression. But since it's not, we're going to pass it over. The one number here that is kind of interesting is the significance, which is equivalent to effectively the p-value. And so that's 0.02. So that tells you that we've got something statistically significant, right? That turns out to be the same p-value that's right down here. And then this line is the line of tremendous interest to us. In fact, I'm even going to highlight it. You don't have to. Highlight it in yellow. And I'm also going to highlight this value because this is also of a lot of interest to us. So why is it of interest? Because this is the independent variable, sales cost, right? It's what's on the x-axis. Notice that the dependent variable, copier sold, is not mentioned anywhere in the regression statistics, which is kind of annoying, but it is what's being predicted. Okay. So let's see what we've got. The t-stat, we want to reference this output, and there's the t-stat. It's the t-stat for the predictor for sales call. Now, the DATP does not give critical values for t, so just use 2 or -2 as approximation. So in other words, when you look at that 2.93, you think, oh, well, that's bigger than 2, so this is probably significant. But you don't have to go with probably, because you do have the p-value, which we'll grab over here. And that for sure tells you that it's significant, because it's less than 5%. So decision about H0 is reject the null. In our interpretation, right, we can say more than that it's significantly different from 0, because we actually know that it's also positive. So the slope is positive. We've now established that. It's positive, not just in our sample, it's positive in the population. All right. Let's look at the confidence interval. So first, what's the slope? Well, the slope is the coefficient of sales cost, so it's that 1.18. And then we don't even have to calculate the confidence interval because it's given to us on this same line. See, there's the lower 95% and the upper 95% is this guy. You'll notice that these appear twice, which again is kind of annoying. Lower 95, upper 95, lower 95. And the reason for that is because for this second set, you could have changed that in the interface. We didn't, but we could have changed that. So that would have been like lower and upper 99%. Okay, let's continue through here. So here in the middle, we're actually being asked to identify the equation, right? It's this equation here, but we want to identify it from this output. So copier sold is equal to something times sales cost, because sales cost is the x, right? Plus the intercept. So what's times sales cost? Well, it's the coefficient of the sales cost. So we just click here and put equals that coefficient plus, and then put equals and plus the intercept. And that's our regression equation. It's exactly the same regression equation that's here, but here it's up here so we can kind of use it later. All right, the standard error for sales calls is right there. It's right next to it, that coefficient, so it's 0.4. So I'll just put equals. And you have to reference all these numbers. You can't type them or you'll miss all the decimal places. Even though they're hidden, they are there. And then the count is the number of observations, which is actually also here. We don't even have to count them. 10 observations. And now we get our graphs. All right. So what's going on here? Here is the sampling distribution of the slope. So again, that's because that's what we're working with is the slope. This would be a slope of 0. We are more than 2 standard deviations. Remember, more than 2 is always a big deal. We're at 2.93 standard errors or standard deviations of the sampling distribution. Our value 1.18 is over there. And that, as you can see here in the standardized graph, definitely is in the rejection region. Back over here, you can see our confidence interval. So in other words, we think that in the population sales calls, the correct slope of the line for sales calls is 1.18, but we know for sure it's between 0.25 and 2.11 at 95% probability. So, a couple more things. Now, the whole reason for doing regression, the reason people get so excited about regression is because it can be used to predict other values for which you don't have points already. And you do that with the regression formula. So first let's put in the copiers sold regression formula. So that's equal to, right, there it is, 1.18, which will lock because it's not in here, times number of sales calls. So this is for a brand new point that's not part of the graph already, plus the intercept, which will lock also since it's not on in this table. And then this gives us the predicted copiers sold for 20, 40, and 60 sales calls. But it's not going to be an exact prediction, so there's going to be a range. And we can get at the range by clicking here on the predicted value minus 2, there's that famous number 2 times, this says SEREG, which stands for standard error regression. In fact, up here it says use the standard error from the regression stats, not the standard error of the coefficient. So we don't use this standard error for the coefficient. Instead, use this guy up here from the regression statistics. Why? Because this is the standard error for the whole model. In other words, for the whole regression equation. So it would tell you how far off the entire equation could be, taking everything into account. And I didn't lock things. So what didn't I lock? I didn't lock this guy. And that should be enough. Okay. And then at the upper bound, it's going to be equal to that number plus 2 times the standard error of the whole model. See, the whole model, these regression statistics, these apply to the whole model up here. Whereas here you got individual stuff. And lock that. And then copy that down. Right? So in other words, you get a prediction, but then you get a range. Prediction interval. For 95% confidence on the prediction. Okay, now we come to some really good questions. So reference the slope for sales calls. So remember, the slope is the coefficient of sales calls. So you can reference it here, or you can reference it here. Doesn't matter, I'll reference it here just so you can see the connection to the DATP. So it's the coefficient. That is the slope for sales calls. The coefficient for the intercept, remember, that's a hard value. That's just where this line would, if you extended it out, where it would cross the x-axis. And it does look like it would cross about there at 1885. All right, for every additional sales call, reference how many additional copiers salesperson is estimated to sell. So this is a clever way of asking exactly the same question. So in other words, that's what that 1.18 means, right? If you make one more sales call, right, you're going to sell 1.18 more copiers. So that means each sales call actually results in slightly more than one sale, on average. So that's pretty cool. It's a way of understanding what these numbers mean. and reference the value of the y-intercept. So that's this number. And here, if a person makes 0 sales call, reference how many copiers are they predicted to sell. Well, if you look at this formula, you can get it, right? In other words, if this value was a 0 sales calls, 0 times, 0 times anything is 0, so it's 0 plus 1885. I don't know why the plus got lost in here. Maybe if I reduce the font, you can see these guys again. There it is, okay. So 0 plus 1885 is just going to be 1885, so it's just going to be the y-intercept again. Reference how much of the variance in copiers sold is accounted for by the model. So this is actually really good. It tells you kind of how good your model is, the R-squared, and that's why it's on this graph. This is basically saying that this model, this regression equation, right, accounts for 52% of the variance in this line, which means there's other factors accounting for the other 48%. In SLR, multiple R is equivalent to, so that's this number here, and it sure looks like it's equivalent to little r. That's in simple linear regression. In multiple regression, it won't be. And that does it. So just to review what we said at the outset, I'm down a point. Let's do one more thing, the correlation. So as we said at the outset, correlation, now is this 0.72 tells you how close these points are to the line, how much they line up with the line. But regression, on the other hand, actually gives you the equation of the line, right? And that equation can be used to predict future values for unknown x's. We can predict future y's, in other words, predict copiers sold for other values of sales calls, assuming that the linear relationship holds throughout. So it's a very, very powerful tool for predicting, and but you can also see how sort of these two play together. Correlation, again, telling you how close the dots are to the line, how close the dots line up with the line, and regression actually giving you the equation of the line, including its slope and y-intercept. And that's it for now. Thank you.